Now, in module 3 of chapter 5, we shall continue the serret ferret formulae and its problems into some different types of examples, and we shall see here that how the curvature and torsion can be calculated for any type of space curve, like on a cylinder or in a sphere. So, we are in a position to find the curvatures and torsion of a space curve for any type of curvilinear coordinate system. So, we shall continue the serret ferret formulae and its applications in this module. From serret ferret formulas, we have a tangent vector, a principal normal vector and a binormal vector. Now, the tangent vector and the principal normal vectors form a plane called osculating plane, and the equation of the osculating plane can be denoted in vector form in the following way, that if on that plane a point has position vector r and a fixed point has position vector r1 and B is denoted by the binormal vector, then the equation will be r minus r1 dot B equals to 0. The plane determined by principal normal and binormal is called normal plane. Its equation can be written as r minus r1 dot t equals to 0, where t is the unit tangent vector. So, we have given a different notation, t as a unit tangent vector, capital N as a principal normal vector and capital B as a binormal vector. So, in vector form, the equation of normal plane will be r minus r1 dot t equals to 0, and the plane determined by tangent and binormal vector is called the rectifying plane, and the equation in vector form is given by r minus r1 dot n equals to 0. So, with the three vectors, tangent vector, principal normal vector and binormal vector, we are getting three planes: osculating plane, normal plane and rectifying plane. Now, let us see the value of curvature and how to find this value of curvature in a Riemannian space. So, here curvature is root over g m n del lambda m del s del lambda n del s, because from serret ferret formula we know that del lambda m del s equals to kappa mu m. So, del lambda m del s into del lambda n del s equals to kappa square mu m mu n, and which gives, if we take on both sides by g m n, then it will be g m n del lambda m by del s del lambda n by del s equals to g m n kappa square mu m mu n. Now, g m n mu m mu n is equal to 1. So, therefore, kappa square is coming to g m n del lambda m del s del lambda n del s. That means, kappa is the square root of Gmn del lambda m del s del lambda n del s. We can also obtain the expression for the torsion tau, which is given by epsilon I j k lambda I mu j del mu k del s, and we can easily find the value of torsion by using Serret-Frenet formula, because we know del mu I del s equals to tau gamma I minus kappa lambda I. This is the second Serret-Frenet formula. So, just taking the product with epsilon I j k lambda I mu j from both sides, we are getting this expression, and from here if we use the value obtained earlier, we get epsilon I j k lambda I mu j del mu k del s equals to tau. Now, let us see that a space curve is a straight line if and only if its curvature is 0 at all points of it, and we shall find the equation of it. So, you are going to find the equation of a straight line in a space. Now, first suppose that the curvature is 0, then from Serret-Frenet formula we have del lambda I del s equals to 0. That is, lambda I has a fixed direction, hence C is a straight line. Now, conversely, suppose that C is a straight line, then direction of tangent to C is fixed, hence del lambda I del s equal to 0. That means kappa mu I equal to 0, which implies kappa equal to 0, because mu I is a unit principal normal vector. So, it cannot be equal to 0, therefore, kappa equals to 0. Now, how to find the equation of the straight line? Let us see this one. Now, from the equation del lambda I del s equal to 0, if we apply the definition of intrinsic derivative, we have lambda I comma k dx k ds equal to 0. And again apply the definition of covariant derivative of lambda I with respect to x k, we are getting del lambda I del x k plus lambda p gamma I p k dx k ds equal to 0, and which gives d lambda I ds by the theory of partial derivatives. We are getting this relation d lambda I ds plus lambda p gamma I p k dx k ds equal to 0. Now, since lambda I equals to dx I ds, if we put the value of lambda I in the above equation, the equation becomes d2 xi ds2 plus gamma I p k dx k ds dx p ds equal to 0. So, this is the equation of straight line in curvilinear coordinates. So, what is the geometric meaning of the torsion? The torsion of the curve measures how far a curve departs from lying in a plane. That is the geometric significance of torsion. That means, it measures the twistness of a curve, and the curvature of a curve measures how much the curves differ from being a straight line. So, it measures the bendness of the curve, how much it is bending. Now, let us try to find the curvature and torsion of a space curve that is defined by x 1 equal to a, x 2 equal to t, x 3 equal to 0 in cylindrical coordinate system, where a is a positive constant and t is a function of s. So, we are trying to find the curvature and torsion of an arbitrary curve in cylindrical coordinate system. We know that line element in a cylindrical coordinate system is given by d square equal to dx 1 square plus x 1 square dx 2 square plus dx 3 square. So, the metric tensors are g 1 1 equals to 1, g 2 2 equals to x 1 square and g 3 3 equal to 1. The non-zero Christoffel symbols of second kind are gamma 1 2 2 equal to minus x 1, gamma 2 1 2 equals to gamma 2 2 1 equal to 1 by x 1, and components of lambda I are dx 1 ds equal to 0, dx 2 ds equal to dt ds and dx 3 ds equal to 0. That means lambda 1 0, lambda 2 is dt ds and lambda 3 equals to 0. Now, as g I j lambda I lambda j equals to 1, we get this expression, and from here if we put the values of g 1 1, lambda 1, lambda 2 and lambda 3 and all these values, we are getting the expression like this, and as x 1 equal to a. So, we are getting the value of dt ds whole square, that is equals to 1 by a square. Now, again from Sennett-Frenet formula, del lambda I del s equals to kappa mu I, we have kappa mu I equals to d lambda I ds plus gamma I j k lambda j dx k ds. So, kappa mu 1 equals to d lambda 1 ds plus 1 2 2 lambda 2 dx 2 ds. Now, if we put the values, we are getting kappa mu 1 equals to minus 1 by a. Similarly, we find the value of kappa mu 2, and which is coming from this expression k mu 2 equals to d lambda 2 ds 2 plus gamma 2 1 2 lambda 1 dx 2 ds plus gamma 2 2 1 lambda 1 dx 1 ds. And if we put the values, we are getting that kappa mu 2 equals to 0. And similarly, if we put all the values in this equation, we can get that kappa mu 3 is also equal to 0. Since mu I is a unit vector, as it is a principal normal vector, g I j mu I mu j equals to 1. So, from this expression we are getting g 1 1 mu 1 1 plus g 2 2 mu 2 2 plus g 3 3 mu 3 3 equal to 1. Now, putting the values, we are getting that 1 into minus 1 by kappa a into minus 1 by kappa a equal to 1. That means, we are getting the value of kappa. As kappa is considered always greater than 0, so kappa is equal to 1 by a. And also kappa mu 1 equals to minus 1 by a, mu 1 equals to minus 1 by a k, that is equal to minus 1. So, the value of kappa is 1 by a and mu 2 is 0, mu 3 0, and the value of mu 1 is equal to minus 1. From second Sennett-Frenet formula, if we express the intrinsic derivative of mu I in the left hand side, we have the expression this one, and for I equals to 1, we are getting del d mu 1 ds plus gamma 1 to 2 mu 2 dx 2 ds equals to tau gamma 1 minus kappa lambda 1, because the k is a dummy index. So, it will run, and from here we get tau gamma 1 0, tau gamma 2 0 and tau gamma 3 0. Since at least one of gamma I is not equal to 0, because gamma i's are the components of binormal vector, which is also a unit vector. So, all the components cannot be 0. So, tau must be 0. That means, this is a space curve whose curvature is 1 by a and torsion is 0. So, C is a plane curve of constant curvature 1 by a. Therefore, radius of curvature is equal to a, and so C is a circle of radius a on a cylinder. Now, let us see another curve where x 1 equal to a, x 2 equal to t, x 3 equal to b t, b not equal to 0, and a b are constants where a is a positive constant and t is a function of s, and we are trying to find the curvature and torsion in cylindrical coordinate system. So, here lambda 1, lambda 2, lambda 3 can be expressed in this form as for previous example, and from the relation g I j lambda I lambda j equals to 1, we can get that dt ds whole square equal to 1 by a square plus b square, and if we find kappa mu 1, the expression is coming to minus a by a square plus b square, kappa mu 2 equals to 0 and kappa mu 3 equals to 0, if we calculate all these values. Now, using g I j equal to mu I mu j equal to 1, we get the value of the curvature, that is a by a square plus b square. Again, if we use the second straight formula, that is del mu I del s equals to tau gamma I minus kappa lambda I, we get this relation. From here we can find that tau gamma 1 equals to 0, tau gamma 2 equals to minus b square by a square plus b square to the power 3 by 2, and tau gamma 3 is equal to minus b a by a square plus b square to the power 3 by 2. So, tau is coming b by a square plus b square. So, here kappa is coming a by a square plus b square and tau is coming b by a square plus b square. So, in the previous example we have seen that the ratio of curvature and torsion is a by b. Now, we come to a new type of curve, that is called helix, and a space curve is called helix if the tangent to the curve at every point of it makes a constant angle with a fixed direction. Now, in a theorem we shall prove that the ratio of curvature to the torsion of a space curve is a non-zero constant if and only if the tangent to the curve at every point of it makes a constant angle with a fixed direction. That means, for a helix the ratio of curvature to the torsion is constant. That means, for the previous example it is a helix on a cylinder, because there the ratio of curvature and torsion is equal to A by B, which is a constant. So, now we shall try to prove this theorem. Let the tangent vector lambda I to a space curve C makes a constant angle alpha with a fixed direction A I, where A I is a unit vector. For the sake of simplification, we are considering that A I is a unit vector. Then by definition G I j lambda I A j equals to cos alpha. Now, differentiating intrinsically with respect to S, we get G I j del lambda I del S A j equals to 0, as del G I j del S equal to 0 and del A j del S equal to 0. Now, using Sennett-Freinet formula del lambda I del S equals to kappa mu I, we get G I j kappa mu I A j equals to 0. Now, as kappa is not equal to 0, so G I j mu I A j equals to 0. Thus, A I is orthogonal to mu I, but lambda I is orthogonal to mu I. We know that lambda I is orthogonal to mu I, because lambda is a unit tangent vector, mu I is principal normal vector. Hence, A I must lie in the plane of lambda I and gamma I. So, the angle between A I and gamma I is 90 degree minus alpha, because A I is making angle with lambda I as alpha. So, it is making angle with gamma I 90 degree minus alpha. So, we can write G I j gamma I A j equals to cos 90 degree minus alpha, and that is equals to sin alpha. Also, we can write A I as a linear combination of lambda I and gamma I. That means, A I equals to C lambda I plus D gamma I, where C and D are scalars and we have to determine these values. From 23 we have, by multiplying both sides by G I j lambda j, we are getting G I j A I lambda j equals to C G I j lambda I lambda j plus D G I j lambda j gamma I. Now, as G I j A I lambda j is cos alpha and G I j lambda I lambda j equals to 1 and G I j lambda j gamma I equals to 0. So, the value of C is cos alpha. Again, from the above relation we can get G I j A I gamma j, that means, we are multiplying both sides by G I j gamma j, we are getting G I j A I gamma j equals to C G I j lambda I gamma j plus D G I j gamma I gamma j, and from here we are getting the sin alpha equals to D. Hence, the above equation can be written as A I equals to cos alpha lambda I plus sin alpha gamma I. Now, differentiating intrinsically, we have del ai del s equals to cos alpha del lambda I del s plus sin alpha del gamma I del s. Now, putting the values of Sennett-Frenet formulae, we get del lambda I del s equals to 0. Therefore, cos alpha kappa mu I minus sin alpha tau mu I equals to 0. That means, kappa cos alpha minus tau sin alpha equal to 0. Now, since mu I is not equal to 0, kappa by tau equals to tan alpha, which is a constant. Now, conversely, let us assume that kappa by tau equals to constant. Therefore, tau can be expressed as 1 by m k, where m is not equal to 0. Now, from Sennett-Frenet formula, we have del gamma I del s equals to minus tau mu I. So, putting the value of tau, we are getting minus kappa by m mu I. Thus, del gamma I del s equals to minus 1 by m del lambda I del s, which can be written as del s of gamma I plus tau lambda I, considering t as equal to 1 by m. Therefore, gamma I plus t lambda I is a constant vector. We denote this vector by a I. Therefore, g I j a I lambda j can be expressed as g I j gamma I plus t lambda I lambda j, that is equals to t, which means it is a constant. So, the tangent vector lambda I makes a constant angle with a fixed direction a I. Hence, the theorem is proved, and we can say that for a helix, the ratio of curvature and torsion is constant. Now, if a helix lie on a cylinder, it is called cylindrical helix, and if the cylinder is a circular, that means it is a circular cylinder, then it is called a circular helix. From the given figure, we can see the structures of helix. In previous two sections, we have learned about Sennett-Frenet formulae and a new type of curve called helix. We have seen that how curvature and torsion can be calculated for any type of space curve, and we have also seen that the ratio of curvature and torsion for helix is always constant. Now, in the next section, we shall see another type of curve called buttoned curves or buttoned mates. So, let us see the definition of buttoned curves. So, in this section, we see a new type of curves, that is a pair of curves which is known as buttoned curves. So, a pair of curves is called buttoned curves or buttoned mates if they have same principal normals. That means, their normals, principal normals are same at the corresponding points. So, let P and P bar be corresponding points on the curve C and C bar, where they have the same principal normal. Then we can prove that this P and P bar, the length of P and P bar is equal to constant. Now, to proving this one, we shall approach in a vector approach, and the tensor approach will be left for the reader. Now, let position vectors of p and p bar be r and r bar. Therefore, r bar can be expressed as r plus a mu, where mu is the principal normal vector, where p bar equals to a. Now, we shall try to establish that this a is constant. Now, taking derivative with respect to s, we get dr ds bar ds equals to dr ds plus mu dA ds plus a d mu ds. Now, dr bar ds bar can be written as lambda bar. That means, it is the unit tangent vector for the c bar curve. Dr ds equals to lambda, that means, it is the unit tangent vector for the curve c plus mu dA ds plus a. Now, d mu ds can be written as minus kappa lambda plus tau gamma. From the Serret-Frenet formula, we can write this expression. Now, taking dot product by mu, we get, now as mu equal to mu bar, so in the left hand side we replace mu bar. So, mu bar dot lambda bar ds bar ds equals to, and in the right hand side we are considering as mu. So, mu dot lambda plus mu dot mu dA ds minus a kappa mu dot lambda plus a tau mu dot gamma. Now, mu lambda, mu gamma are all orthogonal. So, mu dot gamma, mu dot lambda are all 0. Therefore, dA ds is coming to 0, because mu dot mu equals to 1, and here mu bar dot lambda bar is also 0. So, as dA ds equal to 0, we can claim that a is constant. Now, we can also prove that the angle between two unit tangent vectors at corresponding points is also constant. So, let us start with d ds of lambda dot lambda bar, and we are getting d lambda ds dot lambda bar plus lambda dot d lambda bar ds. Now, putting the value of d lambda ds and d lambda bar ds, we are getting by using the dot product that it is 0. That means, d ds of lambda dot lambda bar equals to 0. That means, lambda and lambda. So, as d ds of lambda dot lambda bar equal to 0, we can claim that angle between lambda or lambda bar is constant. In a similar manner, we can prove that the angle between gamma and gamma bar is also constant. Now, this is a very important result, that for Barton curves, the relation between curvature and torsion bears this relation, that is a kappa plus b tau equals to 1. A linear relation between curvature and torsion occur for the pair of Barton curves. Now, from the previous expression, we have lambda bar ds bar ds equals to this one, 1 minus a kappa lambda plus a gamma tau. Now, taking dot product with gamma bar from both sides, we have this expression. And from the previous expression, we get 1 minus a kappa lambda gamma bar plus a tau cos alpha. Now, angle between lambda and gamma bar is sin alpha. So, if we put the value sin alpha here, we get after simplification that A kappa plus B tau equals to 1, where the value of B is minus A cot alpha. Therefore, for button curves, the relation between curvature and torsion is A kappa plus B tau equals to 1. The example of button curves can be seen in the structure of DNA, where it has a double helical structure. So, in the last section of module 3 of chapter 5, we have learnt about a new type of curves, that is a pair of curves called button curves or button mates, and we have seen that curvature and torsion has a relation, a linear relation A kappa plus B tau equals to 1. And also in the previous section of this chapter, in the module number 3, we have learned about helix and Sennett-Fennet formulae. So, we end this module